Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this morning I'm very pleased to welcome you to the Cloud Cryptography Workshop. As most of you know, this workshop was conceived and organized by Seni Kamara and Melissa Chase from the Research Cryptography Group. And they've done a fantastic job of organizing. I'm so glad you're all here. We have a great list of speakers and topics relating to cloud cryptography. So to kick off the conference, we're very pleased to have John Manfredelli, Distinguished Engineer at Microsoft Research, to give us a little bit of an overview and background on cloud computing security. Okay, thank you.
Thanks. Actually, it's punishment. My father always wanted me to be an engineer, and I wasn't, so the title was punishment for something I did. So I want to talk. We actually have two conferences going on at the same time. We have a cloud security conference workshop focused on systems aspects of cloud security. In fact, I tried to have them on so they didn't overlap because I want to go to both. But because of schedules today, they're both on. So I'll be bouncing back and forth. So you've heard a lot about clouds. In some ways, there's not too much new. Grids were a little bit like clouds for a shared infrastructure for computing. They've gotten very popular partly because of scale and partly because people have this sense that they're going to save a lot of money by using clouds. And I'll explain to you the reasoning behind that, which is a little bit flawed. It's mostly flawed around security, but it has a few other problems too. So let me give you background that you all know. There's a tremendous asymmetry between attackers and commercial operations generally, even clients. Where anybody who's under the misapprehension that we got things under control, they're just wrong. There are new attacks every day. If somebody wants to have a targeted attack, they can do it. It's not like they stay up at night saying, "Gee, I wonder how I'm going to do this new one to get poor Or over there if they want something." The clouds offer new uses. And probably the biggest one is just as a huge data store, a common data store where you can bring computing to them, look at an enormous amount of data, whether it's social networking data or search data, and analyze them. The most corporations, if you ask Bill Gates, he thinks a huge part of IT will move to the cloud as cost saving, so there will be a big business. Even for somebody like the government, just being able to use the shared infrastructure for something simple as communicating, bandwidth, is a good deal because the cloud providers get preferential rates on things like that. Many people, including many of the applications you're going to think about in this conference, really have to do with clouds and clients interacting. It's not just about IT running their payroll or whatever they want to do in the cloud, but some service that has a client side on a mobile phone, on a PC, on whatever, and a huge service in these clouds somewhere. And so the whole, actually people really do now have to think about distributed security. They had to ever since they plugged in the internet, but now it's, if you're really going to pay attention to clouds, you have to do that. And there are geopolitical considerations. Some are obvious, some are not. Privacy concerns in some countries are different than others. If you're in a data center and it's being used as a botnet, you run the risk of being closed down because somebody has to find the botnet, and the cloud provider hasn't isolated them well enough to say that thing over there. And there's certainly been occasions where that's happened. Also, cloud infrastructure is usually pretty homogeneous. There was a case where Amazon, and this wasn't even through a malicious attack, went down for 18 hours because there was a single accidental flaw in a protocol that was used everywhere. And somebody accidentally triggered it. It was called the packet of death. But even with that, there's really quite a strong drive to the cloud because of this alleged and again, it's not completely crazy, tenfold cost benefit. The final thing is when you control your own computing infrastructure, you're more focused on what you're trying to do, the mission, the problem. And so whatever you do, the security is tailored to the thing you want to do. If you're not too worried, you do one set of things. If you're very worried, you have a lot of control over what runs where, when, how you audit it, how you look at it, what you encrypt, how you share it with other organizations. But in the cloud, just as in the PK infrastructure, the focus is on cost savings and brand and marketing. So sometimes you're in this wacky situation where you say to somebody, that's a very high, that threat is really bad. And they say to you, it's not so bad because when they get hit, they won't know about it. So a security guy goes crazy or something like that. But again, for brand preservation, there's some thinking that that's not quite as bad as having all your data stolen. So there are many interacting things. So here's the economics. This might be interesting just as a very rough guide of why people think clouds are going to be a lot cheaper. So if you have a very large data center, let's say a couple 100,000 machines, the cost of buying the hardware, because you have a good, you're a big customer, you have preferential rights, and the savings you get from power, there's a fourfold differential among the power rates, and you obviously get the best at the data center. In fact, typically you put the data center close to a power source, and the argument for a good rate is they lose less power in transmission. And bandwidth costs, those are low. So altogether, the total cost of ownership of a server in a cloud is less than half of what I would go out or some small company would go out and buy a server for. Maybe even a little less. So there's a twofold improvement there. The second improvement has to do with utilization. The argument is that when I run a server in the cloud, I can get about 4 times as much work by sharing loads on it. 2 to 4 times, depending on how you talk to. And 2 times 4 is 8. Well, there's the 8-fold savings. And in some cases, it really does work for standard services like search or mail, which are pretty undifferentiated services. Everybody kind of does the same thing, and just that works out pretty well. It works less well when anybody cares about security. So in data centers now, this is probably the right crowd. This drives me crazy. I don't know a data center where if you want to run a secure service, you don't hand the data center operator your private keys. There's something wrong with that. There's several things. But that's actually the way it is now. This mostly was for the other talk, for the non-believers, the people who think that security basically is under control. I told my wife a couple of days before the conferences I'd go to the register and find the latest 5 stories about what bad things happen. And this is prejudice towards Microsoft, or against Microsoft, I guess I should say. So again, emergency patch for Windows. It's a serious problem. I think it just got patched yesterday. What day is today? Wednesday? I think it went out with the Tuesday patch. BP, while they're trying to protect their brand, actually was infiltrated. So some information they didn't want out actually got out from an attack. The iPhone had a Trojan attack, which you'd expect. Citigroup, which really is well-intentioned. They want to save their own money. They're at risk when people use their application and something bad happens. An attack on the 27th. Everybody remembers the Google attack. It's infamous, and that was a cloud attack. Windows, if anybody thinks the problem's all solved, Tavis at Google found a bug in Windows, an escalation of privilege bug that was there basically since the start of Windows. Flash is just too easy a target, so we won't talk about that. And I got this graph of attacks from our malware center. I don't even know what the scale is, but you can tell it's bad. It's very bad. So the problem, even on a client machine, on a server, one you control, there are 2 sets of problems. The first set of problem is the hardware, what it can isolate and where. There's some pieces of hardware which are just not well suited to isolation for competing adversarial applications. The screen is one. But that pales in comparison to the software problem, which mostly has to do with us using OS legacy, which grew up in a time when time sharing, if there was any security at all, it was the time sharing model, where there was a single administrator who knew everybody who used the machines, who actually personally installed and understand all the important software, and knew the people who were going to log in, gave them their logins, which is, of course, not the world we live in at all. PCs made that a little bit worse because it went from several people using the same machine to one person using the same machine, and why were you protecting yourself from yourself? And then people plugged their machine into the wall to the internet, and things went bad. OSs are huge, and everybody gets everything for some reason. Configuration is very difficult. I personally don't know how my machine is configured, and I try to understand from time to time. If you look in your Windows root store, you'd be frightened. But the major problem is a vulnerability anywhere in this stack affects everything, which is very worrisome in a shared environment like cloud computing infrastructure. In most cases, I don't worry too much about attacks which involve physical possession. But in the cloud setting, that is a problem. The data center is run by insiders. You never see them. They're not loyal to you. They're loyal to the organization that hired them, or possibly somebody else, which is even worse. So insider attacks in these things are major problems. And people can dismiss them in an enterprise setting. You can't walk away from them in a cloud data center setting. Still, the internet's great. Collaboration, sharing. I mean, we all get papers that are posted on the internet. I mean, it's really a wonderful environment to get information. So you sort of don't want to give that up. The commercial infrastructure with all these problems has moved to clouds, and it's going to take those problems with it. So what are we going to do about it? Is sort of the question. I was on a government panel. I think and maybe people in the room will the usual way to do with security, I would call it phenomenological. Or ad hoc is probably a less classy word for the same thing. It's people sort of try to prevent attacks by noticing what the last bad thing happened, fixing that. There's a lot of research in detecting attacks. Again, it's very interesting. A clever person, it's very hard to detect attacks. So the research is quite interesting, but again, the success rate isn't great. You wouldn't want your life to depend on always finding out when you got attacked. Then they try to mitigate the attack. Okay, we can't really fix it, but we're going to do things so it's hard for people to exploit it. And finally, recovery. So when a disaster happens, where's the CD that we go reinitialize everything with? And these are all valuable, actually, mostly for analysis to see what's around. So I won't list all these, but one example is address space layout randomization, which sort of combats a little bit of the homogeneity problem. It will not stop all attacks. But the nice thing about the randomization is even if you only see 10%, 1% of the attacks because the randomization causes them to fault some way, you can detect attacks. They're a very sensitive indicator of attacks in the wild. They're not a way to stay safe, though. They're just a way to find out what's going on. So we're losing. In both conferences, the question is, what can we do in a more fundamental way? If this were, if people treated security as a science and not the sort of ad hoc phenomenological thing they do. And so you can look at a couple of models. The physics model, which isn't completely appropriate, it's probably nature is subtle, not malicious. The world we're in, people are not necessarily subtle, but they are malicious, and they often get away with it. So the role of adversary enters, but that doesn't mean you should give up. Economics is in that same model. So I went back to my old physics books, and if you just sort of glance at what's important to scientists, they really they observe and guess, which I could say we're doing now, but they want nice theories that predict and explain phenomenon. You shouldn't be able to make money as a scientist for predicting the past. Theories have to predict, phenomenon before they happen, which is apparent, is not always true in security. And they look for simple laws that are comprehensible, so you can analyze what's going to go on and make the prediction. And finally, they're verifiable. I mean, despite all the crabbing among physicists, if you have an experiment that disproves a theory, you probably don't get the kind of crap you'd get if you were in a political debate. It's just, didn't work. Too bad. So the goal, generally, for security in the cloud is you want to protect both from the classic external attacks that we see now, but also internal attacks, insider attacks. And the environment has changed. Now you're at the mercy of insiders. You can't deny it. It's not exactly a hardware problem. In some cases, it's very hard to protect hardware if somebody has physical possession. But, for example, in a data center run by somebody, Microsoft, who doesn't especially like being sued, physical possession is less of an issue than security. You can have cameras on the machines all the time. There are very few people. And in some data centers, you roll up the truck with all the computers, and you never open it. When things break, they're gone until you throw away the container. So physical security can be a problem, but it's not as big a problem as software. So I'd like to go back and say, well, what do we want from these data centers? And these are the sort of the buzzwords you'd all look for. But you'd like a simple model for why whatever you're going to do provides them. Not a complicated, we did this thing here and did this thing there, and maybe if everything works out, we won't get hurt. So the first conference looks at this systemically, and their basic model is what can we do so when you run your software on a machine, there are three properties. You know exactly what software and hardware you're relying on for security. You can measure it in your software somehow, cryptographically, actually. The second thing is when you're sharing resources, let's focus on the CPU, they really are isolated. And again, there are still issues with things like side channels, but again, many of them can actually be addressed by hardware, by assigning bandwidth, that sort of stuff. But really isolated, not what happens between one process on Windows or Linux, for that matter, and another process. Like, they're isolated. Another thing is the program, not the people, should have secrets that only they see. The guys in the data center ought not to see your secrets. And finally, you ought to be able to do this in a manageable way, and you should be able to verify this cryptographically over the internet. So in the system setting, this is one solution which would make clouds believable for somebody who had sensitive data. And again, once you have this environment, you never let anything out unencrypted outside your partition. The disks always contain encrypted data. That's it. You always transmit stuff encrypted. So if you mess up, it's your own fault. Correspondingly, and this is an example, I think much of what you'll talk about goes to another problem. Is let's just give up. Let's say the data center is run by Joseph Stalin, and we still want to get some useful work out of it. Is there some simple guarantee, some simple way, and are there some simple things we can do to do useful work? And I think it turns out there are a lot. They'll get better, but even the simple ability to store stuff, because the cloud is quite good at communication and storage in an encrypted manner, get to it from anywhere, with the additional ability to search it, that's actually a huge benefit. And if your data center is run by Stalin, you don't worry so much because you're also using a data center run by Chairman Mao and somebody else, whoever the bad American guy is. So there's some redundancy. So that's the goal of this meeting, and I think it's actually quite important. I'm a little bit skeptical about the hype. In fact, I'm a lot skeptical about the cloud. But the cloud will have a lot of benefits. It will eventually do many of the things people hope they do, but not without being safe. And right now, they're not safe. So I look forward to the conference. I will be in and out today, but I will mostly be here tomorrow. And I want to thank you all for coming. I'm really glad they're being recorded, so the ones I missed today I'll get to see. So.
Post a program to the other conference? Maybe some of us will want to see that.
Yeah, maybe. Actually, it turns out, so the first day it was quite different. The second day, we're going to talk about TPMs, one of the things that let you boot these things. And we're going to talk about searchable symmetric encryption, but you're going to hear that talk here in this session too. We duplicated it. So I think, yeah, you're welcome to come, but I don't know that, I think we've arranged it so that you won't have to generally. Okay?
Okay, so when I prepared the talk, I wasn't sure about what the audience will be, so I kind of prepared like the first half to be kind of more for wider audience, and the second half more technical. But then I can also plan it for a little bit more time, so maybe the second half will come shorter. Anyway, so what does this code do? So if you know C, that you can stare for a few minutes and you can see this program basically counts the number of primes from 1 to 100. So there are two loops, one inside the other. It checks iteratively. It's very easy to see. Yeah.
It seems like it's still cut off. It's the left. We should,
no, I think about, yeah, it is cut off a bit to the left, yeah.
Is it definitely supposed to? I don't know. Well, it's up to you. You can go if you want.
In fact, there's, maybe we can just run it in this mode. Oops.
Oh, this is good.
That works, right?
Oh, you mean like this?
Yeah, in case nothing is cut off. Okay. Even this works. Okay. So what is so what does this code do? So it's hard to see, but it's kind of hard to, if you start it, it's hard to see what this code does. But in fact, this code does the same thing as the first code. Both codes count the number of primes from 1 to 100. And in fact, this second code it was generated from the first code via mechanical transformation, which is a very simple number of syntactical operations, changing names of variables, turning loops into recursion, etc., stuff like that. So this is the process of program obfuscation. And what is program obfuscation? So it's many different things to many different people. From one point of view, program obfuscation is an art form. It's an art of writing unintelligible or surprising code. And in fact, there are several yearly contests and lots of creative code out there. So here's the winning entry in the 15th International Obfuscated C-Codes contest in 2000. So the thing starts in 85, I guess. So the author said this is a C program. It's hard to see from far away, but instead of making one self-reproducing program, what I made was a program that generates a set of mutually reproducing programs, all of them with cool layout. So if you feed it with itself, you get another face, and etc. So this is one way to use obfuscation. So here's the winning in the same contest 4 years later. So this is an operating system, maybe a bit smaller than Windows, but so this is a 30-bit multitasking operating system for x86 computers with a graphical user interface and a file system, support for loading and executing using applications in ELF binary format, with graphics and a command shell and a text editor, etc. So this is another cool thing. Okay, so it runs. Okay, so this is one way of looking at program obfuscation. So, but also program obfuscation can be something else. So it's also a useful tool for hackers, right? So if you're a hacker, if you want to attack a system, you want to hide what your program is doing. And in fact, many viruses, worms, and malicious code try to hide their code by using a number of techniques. So some of the techniques are, make sure that the code that is running on your computer is different than the code that is written on the disk, and the code may even modify itself as it's running, and maybe even keep only the one piece of code that is running in the clear, and the rest is encrypted, and the keys are changing all the time by the program itself. So there are all kinds of different techniques to hide the code. And in fact, there's a web page that was a blog by an intrusion prevention system, something that a student at Tel Aviv found. So this is what it looks like if you just read it. If you just look at the web page, maybe you think it's maybe a picture or whatever, a JPEG. But it turns out if you what this is lying underneath here is basically it's a redirection to some malicious website. As soon as you click on some pixel on the screen or some range on the screen, it redirects you without realizing to some malicious website. So that's another thing that obfuscation is being used for. But also obfuscation is also a business for the point of view of the good guys. So if you look on the web and you look for program obfuscation, you'll find many vendors that are willing to sell you obfuscation code. That's code that is it's compilers that are going to turn your code into something which hopefully has the same functionality, but looks unintelligible to others. And there are very many good reasons to do this if you're a software vendor. So you want to put software up on the web or in the public. So you want to protect your IP. You don't want people to understand what your code is doing. You want to maybe prevent people from modifying your code in intelligent ways. You may want this obfuscation may be a good way to stop hackers or to slow hackers. So good reasons to obfuscate code. And people are doing it. So there are many techniques again for obfuscation out there. Those commercial obfuscation tools. So one set of tools is to obfuscate the source code. So you do variable renaming and you change the control structure as I've seen before, and you maybe do some higher level semantical changes in your program. And another set of techniques is to obfuscate the object code, forget the source code, and then you just look at the machine code and you add redundant operations, you variate opcodes, you variate modes. The same operation can be done in many different ways. Again, you encrypt unused models, etc., etc. And but most of the techniques are proprietary, and the name of the game here is security by obscurity. So I'm going to tell you what I'm doing, and you will never be able to understand. Or never, but to slow you down at least. So people are doing it, but let's think for a second, what could we do if we really had a good, really secure code obfuscation mechanism? I think it could be really great. It's a really cool thing to have. So assume we really could take software and obfuscate it to make it look like tamper-proof hardware, right? So you can't really make it like hardware because you can always duplicate it. Hardware you cannot duplicate, but forget that, and let's assume that you can prevent everything else. So we could do lots of cool things, right? So as I said before, we could publicize code without fear of misuse. So this is great for code distribution for download. Also great for cloud computing, right? I could give my code to the cloud. He would run it for me, but will not be able to understand anything from it. How it's run, won't be able to meaningfully modify it. And so even if I don't have secrets that all the randomness is public, I don't have any secrets that the cloud doesn't know, even then he won't be able to do things in a meaningful way. And furthermore, if I actually do have some secrets and say run the program or write my program in such a way that the output is encrypted and only I have the key, then the server won't even know what he's doing, right? So if I could obfuscate everything in an efficient and effective way, security of cloud computing would really be not a problem.
So you assume that actually it is a privacy homomorphic, right?
So fully homomorphic encryption is a technique that doesn't go all the way to obfuscation, but it's very useful.
Obfuscation in your definition is more general.
Then right. Exactly. So it's more general than fully homomorphic encryption. I'm saying in general, I can take my program and write the input in a I don't even have to have a fully homomorphic encryption as a technique explicitly. I can just write a program that takes encrypted inputs, has a key in the clear in the program, has the key, decrypts, run the computation, encrypts again, and then that's a program with a key inside the program in the clear, and then obfuscate it. So it's the same functionality, but now the key is obfuscated, nothing you can do. So clearly, fully homomorphic encryption is a very useful technique here, to do this. But as just as an idea of what you're after, that would be great. So that's one set. So we can stop here, right? But because we are in a cloud computing workshop, but there are other applications. So you could publicize data with putting curbs on how it's going to use, right? So you think of putting medical records online, but you just want to be able to allow to use them in certain ways and not others. So you can just do it, right? Because you data together with the obfuscated codes that does the control. You could pretty simplify secure distributed tasks, right? Because I want to run a protocol, I want to do, say, a voting among a number of people. I want to poll their votes, and I want to get the results. So I just write a piece of code that gets from each one its password and its vote, and just accumulates a tally and gives me outputs a tally. I obfuscate it, and I let the people run it, one by one, and then in the end I get the result. So it becomes almost trivial. Also has some nice game theoretic properties. So there's a paper by Mikhail and Shell that actually uses exactly this idea without calling it obfuscation. Assume there is a trusted token that passes around. And that has nice properties. So we can also, if we want to go further afield into cryptography, we can turn, we can get public key encryption from symmetric encryption and signatures from MAC and random functions from pseudo-random functions. So we can get all those beautiful things. So in general, obfuscation is an immensely powerful tool. So you can do many things. But unfortunately, all the techniques that are out there that we know are all heuristic, and essentially they're all eventually reversible. There's no real security there; just annoyance to the hacker, right? And in fact, the common wisdom is that all obfuscation methods are doomed to failure at some point or another. That's common wisdom, and actually, it's been written very nicely by this technical writer. So secure obfuscation is unlikely. A computer ultimately has to decipher and follow software programs through instructions. Each new obfuscation technique has to abide by this requirement, and that will be reverse engineered. The computer has to run the program. Eventually, just look at what the computer runs, you'll be able to understand what's going on. So that's the common wisdom. And is it true? So can we have really unbreakable obfuscation? And in fact, since we are cryptographers and so we like to think about things mathematically, not just physically and empirically, how really define what obfuscation means. So here is so there's been a lot of work in the cryptographic community in the last 10 years or so on obfuscation and in a rigorous way. And here's a definition that was proposed: virtual black box by Barak et al. So an obfuscator is a compiler. It's also essentially inherently a randomized compiler that has the following properties. So first, it preserves functionality. So for any program P, the output program Q, which is after running the obfuscator P, has the same functionality, maybe except with negligible probability over the choices of the obfuscator. And it preserves running time, so that the Q doesn't run too much slower than P. And then there's this other property that actually it obfuscates. And what does it mean? So very intuitively, at the high level, it means that having full access to the code of Q should not give to the adversary any advantage, any computational advantage on top of having Oracle access or black box access, or to secure tamper-proof hardware that runs the program P. And he's tried to codify it in a mathematical way. So here's an attempt. So for any point, like in the tradition of cryptography, for any polynomial time adversary A, there exists a polynomial time simulator, another adversary S, or machine S, such that for any program, whatever the adversary outputs after seeing the obfuscated version of P can be output by S after having only Oracle access to P. But this is obviously too strong, right? Because the A could just output its input, which is the obfuscated program, and the S can never output a program, any program that has this that has the same functionality. And if this program does anything useful, then of course those things will be distinguishable, and so this is too strong. So let's settle for something slightly weaker. So now let's say that the adversary only tries to compute some predicate R of the program. So it just outputs one bit. And then you want to say the simulator does the same thing. It manages to predict this predicate in roughly the same probability. Or equivalently, if the probability that the adversary outputs 1 is the same as the probability the simulator outputs 1. And this is called virtual black box. So, in fact, the main result of this paper that even this weakened definition is unachievable, right? So you cannot have compilers or obfuscators that have this property. So, in the interest of time, I'm not going to go over the proof. Although it's rather simple. So what the proof actually shows is it says two specific or one specific class of programs that cannot be obfuscated. And essentially the idea there is to do some diagonalization, and the fact that the adversary has some code for the program, no matter how obfuscated, it allows you to do things that the simulator cannot do, having just Oracle access, in a similar way to the way we argued against the definition that allowed the adversary to output long strings, but in a slightly more sophisticated way. But anyway, so the conclusion is that there exists a family of programs that cannot be obfuscated. And the idea there is to use the fact, again, the difference that the adversary has some code that runs the program, no matter how obfuscated, and the simulator has nothing, just Oracle access, and there is a big difference there. But what does this impossibility mean? So definitely it resonates the popular belief, right? So that's why it's kind of very convincing. However, if you look at it a bit more closely, then what it only shows that certain classes of programs cannot be obfuscated, right? That means that it rules out a generic compiler obfuscator that can obfuscate everything, okay? But still there may be other, specific classes of programs that can be obfuscated. And also, it only considers a relatively strong notion, this virtual black box, and this equivalence to tamper-proof hardware, and essentially the impossibility uses in a very strong way this particular feature of the definition. So this leaves open again the questions of what about obfuscation of specific classes of programs, and what about weaker notions of obfuscation. And indeed, there was a lot of research in the last 10 years or so, or 9 years, on different variants of obfuscation. So just to say very briefly, so the one direction for research is works that obfuscate specific program families under different variants of notions. And then another set of works showed connections between obfuscation and other cryptographic tasks, between obfuscation and encryption, signatures, and other things. And then the other set of works to extend these impossibility results to have stronger impossibility results in other cases, if you require more visible things like auxiliary information, etc. And then there was another set of work that investigate alternative notions, so relaxations, additional features, etc. So there is so this is essentially the works that have been done. So in the rest of this talk, in the remaining time, which is not too much, I'm going to actually have some time. I'm going to concentrate on a very specific thing. I'm going to concentrate on the original virtual black box definition, although it's strong, as I said. And the silent characteristic of this definition, which actually I didn't say before, is that you need to obfuscate any program in the family. So that's the definition there said that the obfuscate should work for any program in the family. And this requirement for any program in the family, although it's very natural in the context of obfuscation, this is what you would really want, actually makes the definition very strong, as we'll see. And here we can only do a few things, but there are actually things that we can do. And this is this point of Obfuscation and Friends. And I'm going to talk more about this. So here is the motivation for the problem. So for point of obfuscation, so assume so Alice wants to post a puzzle in the newspaper. So those puzzles, we'll find the differences between the two pictures, and you want to post it together with a solution. So that those who solved the puzzle can verify that they found the right solution. But the solution should not be in the clear. Only those who actually found it themselves should be able to verify, right? So it should be somewhat obfuscated. So like here, right? Here the solution's here, but it's obfuscated because it's written backwards. I mean, upside down. But Alice wants something slightly better than that. So again, what we want is that correct solutions will be accepted and incorrect solutions will be rejected. That's the program. And no information will be leaked by the program other than the ability to check different solutions, right? And so how do you do that? So this is really I'm saying okay. So assume that we had an obfuscator for the following family of programs, which I call point programs. So here's a program in the family. So it's a program that has a value A in its belly, and then for each input, it just checks whether the input equals the value in the belly and says yes or no. Okay. So that's the program. That's a family of programs. For each A, there's a program for A. Then if we had an obfuscator for this, then Alice could post an obfuscated version of IA where is the solution and be done with it, right? On the newspaper or in the cloud or wherever you want. And there's the functionality preservation implies that it's going to be okay, and the virtual black box is going to imply that it's secure. So nobody learns anything other than access to the black box for this. So in fact, it turns out that this we can actually construct, okay? In fact, we could construct it before we talked about obfuscation. It was just called differently, but here's the construction. So let G be a group of large prime order, and then what I'm going to do, I'm going to set the obfuscated version of I sub A. So in shorthand, it's going to be the pair R and R to the A, where R is random in the group, or more precisely, if you want to write it in the program. So here's the program. So you have two constants now. One is R and the other one is R to the A. Instead of having A in the clear, you have those two constants. And basically, when you get an input, you check whether R to the input equals the B. Okay. So this is an obfuscated version of that point program. Okay. And now the challenge is to show that this is really the case, to actually prove that this is the case. So actually, I was planning to spend a few minutes on the proof just to get an idea how those things look like. So let me try to do it. So functionality preservation is clear. So it computes the right function, this program. And we show a virtual black box under the strong version of the decision of Diffie-Hellman assumption. And what's this strong version? So the decision of Diffie-Hellman says that if you have R to the A, R to the B, and R to the AB, it's indistinguishable from 4 random values or elements in the group where A and B are chosen at random. And here I'm going to require this is the case even when B is chosen at random, but A is chosen from any distribution which is well spread, which has enough in entropy, right? It's have super logarithmic in entropy in the security parameter. Okay? So I'm going kind of on a limb, and I'm saying as soon as A, of course, when A has only polynomial or only logarithmic mean entropy, so there are some values that have some non-negligible probability, then of course this thing is false. But I'm saying that as soon as you have enough in entropy, it's okay. So this is true in the generic group model, etc. But it's a strong assumption. So how do you prove it? So it's 2 steps. So the first step is to show that this program, this obfuscator satisfies some slightly weaker notion of security, which I call this, not weaker, a different notion of security, which is called, I call it distributional distinguishability. So what does it mean? That for any well-spread distribution, D again, any distribution with enough mean entropy, if you get an obfuscation of IA where A is taken from D, it looks to you as just the same as an obfuscation of IA where A is random, uniform, okay? So any distinguisher cannot tell the difference between the 2 things. So if we look again, what it means in our case is that the pair R to the A, where A is taken from any well-spread distribution, looks like R and R to the A, where A is uniform. And this follows directly from the assumption before, so it's immediate. So now the hard part is to show that from this DI, you can get a virtual black box with a simulation definition. And this is actually generic, has nothing to do with this specific scheme. It's a generic statement that any point obfuscation that satisfies DI already satisfies VBB. So what do I need to show? I need to show that for any adversary A, there is a simulator such that for any A, any single specific secret A that is fixed, the probability that A outputs one given obfuscation of IA is the same, roughly the same as the probability that S outputs one with oracle access to IA. So how do I do that? So what can S do, right? S has this oracle. So this that gives you one point that you have no idea, and otherwise tells you 0. So it seems like it's useless, right? This oracle. So what does CANS do? So what it can do, it can say choose a random point R, and compute obfuscation of IR, and run A on this, and hopefully it's going to be okay. It's going to look the same. But it's not going to really work, right? Because any A for any A, remember that actually there's little a and big A. So for any little, so this has to work for any little a, for any fixed a little a. But the point is that any adversary big A can always have some values of A in its belly and just ask and just run the obfuscator program on these values, right? And if our fixed input happened to be one of those values that the adversary asked for, then the simulator will not work because its simulation will not work. But intuitively, this is not a real attack, because this is really using this program as a black box, so we should be able to get around it. So the claim is that this is all that the adversary can do. The only thing that the adversary can do is check the program on some fixed polynomial number of A's. And the proof is easy given this DI. But assume that assume that there is an adversary in a super polynomial set T such that A can tell the difference between obfuscation on values in T versus obfuscation of values not in T, right? So it's where T is super polynomial side. Then we can, of course, contradict distribution, can contradict DI because we'll just use a distribution which is uniform over T. And since T is super logarithmic, this distribution has enough entropy there. And this adversary can tell the difference between something uniform in T and versus something totally uniform. So therefore, we know that for any adversary, there exists such a set T. And now the simulator is in business, because now what the simulator will do, it will essentially, basically, he has this adversary, and with this adversary comes, non-uniformly comes this set T. So what the simulator will do will just ask this adversary, basically ask all this, the simulator will ask its oracle on all the points in T. If it found the right point, then simulation is easy. It just gives the adversary an obfuscation of IA for that point. Otherwise, it can just give the adversary what it wanted to do before, an obfuscation of a random point. And this will work. Okay?
How do you define T? I'm confused. So what's the formal definition? So you're given the attacker and you need to define T. So how do you define T? You're saying A belongs to T if and only if A outputs 1 or what? So there's a value which is a mean value for the adversary would output for when he's getting of IR for random value. So there is a specific value that's it's 0.4. Yeah.
So I'm saying T is the set of all those values that on which the adversary says something which is significantly different than 0.4. And I say T has to be polynomial for any A. Otherwise, I contradict the other one. Anyway, so that's the proof, essentially. Okay, so this is one construction, and in fact, there are other constructions for point obfuscators. One by Hotek from very strong one-way permutations, and other ones from other assumptions from strong versions of LWE, but those two actually don't get all the way to for every input, but only needs some distribution on the inputs, so it's slightly weaker. But there are constructions. And another question is, all of this construction needs strong assumptions. The question is that inherent? So it turns out that it is to some extent. So again, it's the results by Hotek that if you have point obfuscators at all, then there do not exist a non-trivial or sub-exponential time algorithms for circuit SAT. And if you have such obfuscators which are public randomness, I mean, there's all the randomness the obfuscator uses is put up in the clear, which is like the ones that we saw is like that. Then there exists super strong one-way functions. So one-way functions such that for any adversary can invert them only polynomial number of points. Okay? So it inherently requires strong assumptions, even do this small obfuscation task. Okay, so this looks like kind of like it's a nice game, put puzzles in the paper, but what is it? Maybe it's not very useful. But it turns out that we can use these ideas to do some other things. We can do, for instance, here's one simple thing that we can do. Instead of checking if your input equals some value, maybe we can check if a substring of your input equals some secret value. So now I have a hidden value in my belly, and I want to check whether there exists a substring in the input which equals my hidden value. So why is that important? Why is that interesting? So think that you're a security vendor, and you want to put a firewall vendor or whatever, so you want to put on some server on the net an algorithm that tries to find viruses. But you don't want to give the virus to the server because you don't trust the server. You just want to allow the server to find the viruses for you in case he finds it, but have no information about the virus. So of course you can do that, right? Or the server or the cloud or whatever. So this is a kind of a very primitive secure cloud computing application, right? So you let the cloud find viruses for you. So something else that you can do, so you can extend this instead of checking if your input really equals the point. Maybe you want to check that your equals is close to the point by having distance or something, and this can also be done. But I think this can be done. This cannot. At least this work doesn't talk about this definition of for every input. It needs some distribution. So it's really interesting to see if you can actually extend it. to every input. But so this is something else that you can do. You can extend it to more structural functions. You can do hyperplane membership. So assume that what you have in your belly, what you keep in your belly, is a set of points in some d-dimensional space, and you want to accept all those inputs, all those vectors that are orthogonal to your vector, right? So all the vectors on the hyperplane that's orthogonal to your vector. So that's something that you can do. There's more structure, and using similar techniques. And in fact, you can use this to get signatures with some strong properties that are resilient against leakage. This doesn't do as well as the best constructions that we have, but it's something for signatures with weak keys.
So analysis works only for M order of 1.
Yeah, M is MC. Yeah, M is T. Yeah, it's a dimension. Yeah, sorry. Yeah. So something else that we can do. I'm running out of time, but something else that we can do is instead of having a program that that just keeps one secret in its belly and tell me yes or no, I can have a program that keeps two secrets in its belly. A and B, and if I give it one secret, it give me the other one, right? Yeah.
Over here, this is called an Easter egg.
Okay. Yeah. Okay. So Easter eggs. Okay. So why Easter eggs?
On Easter, they go search for eggs all over the place.
Right.
They used to hide it in code all over the place until the customer got mad.
I see. Okay. I see. Okay. Okay, so you can have Easter egg. That's actually a good alternative name. So the Easter egg functionality. So again, I keep this hidden value in my belly, and when I get the key or the trigger or the secret that I expect, then I release my my secret. And you can implement this in a kind of a modular, straightforward way. From point obfuscator. So what do? So what I publish is so assume that I have a point obfuscator, a way to obfuscate points as I had before. So what I'm going to do, I'm going to publish n plus 1 point obfuscators, and then what's going to be? So the first one is going to be a point obfuscator for this point A. The trigger before, and the other ones are going to be obfuscators of either A if the bit of B is 1, or of some other random point if the bit or the corresponding bit of B is 0. Okay, so now if I have the right trigger A, I can first run the first one to make sure I have the right trigger, and then I can just run one by one all the other ones, see if I fail or succeed, and therefore I learn the corresponding bit of B, right? And if I don't have A, then I'll learn nothing from this. So that's a way to do it. And the nice application for this is to do this this nice thing that we all know how to do for 30 years already, which is symmetric encryption, right? So because basically what I'm going to do, the encryption of M under key K is I'm just publish the obfuscation of I KM. So it looks a bit ridiculous to go back to encryption with all this, but it turns out this encryption is not so ridiculous. It's a very strong encryption. And in particular, what it gives you security against, again, leaky keys, against weakly distributed keys, and also give you security against key-dependent messages. So even if the message it depends on the key, that's only those things that have been recently studied. Turns out you can get all those things from these digital lockers or obfuscation of Easter eggs, and it turns out that this is actually almost the same. So if you can go back and forth, but actually you can get more. So you can get even encryption which is both at the same time secure against weak keys and key dependent and all the mix of those things. But turns out I was cheating a bit. Let's try to run for like 3 more minutes. Yeah. So I was cheating a bit in this construction that I showed you before about Easter eggs. This construction doesn't quite work, as I said, because remember what I did? I just put there a bunch of obfuscations of values out to you. And I kind of like assumed, I made the quick conclusion that if one of them is secure, then many of them put together are also secure. But turns out that this is not so easy. And in fact, it's not true in general. So you can actually construct one obfuscator which satisfies the definition, but if you have several of them, one after the other, it'll stop being secure. And in fact, we don't have any construction of one obfuscation that we can prove that it's composable in this way, under the notion of virtual black box. However, but we can actually, there's a way around it. So we can relax this virtual black box notion a little bit to allow for unbounded simulators. So now the simulator is going to be computationally unbounded. But it's still going to only be able to ask polynomially many queries to its oracle, otherwise the whole thing becomes ridiculous. And we call this virtual gray box. So it's a weaker notion of security for obfuscation. However, this notion, we can show that this RR today construction from before is actually composable VGB, not VBB. So that's great. And then it turns out that this VGB, or virtual gray box, is not so idiotic because it actually suffices for all these applications for strong encryption that we had before. And in fact, it also implies that we also have this Easter egg functionality, implies also encryption which is resilient to related key attacks, right? So I have an encryption under a key K and under a key which is related, K plus 1, K plus 2K, whatever, it's still going to be secure. And this works going to appear in this crypto. Okay, so I'm really running out of time. So there's this other set of requirements from obfuscation, which is non-malleability. So I want to be able to make sure that a program that I have cannot be changed in a meaningful way to another related program. So this virtual black box, it seems as if it guarantees that because the simulator cannot do this with the Oracle access, change the functionality in a meaningful way. So therefore the adversary should not be able to do it too, but it turns out that it doesn't really. You have to make more requirements and you can do it and you can define it and you can construct it, but only we can do it in a very limited way. And I think there are lots of interesting questions there how to do it. And that's almost it. So one set of questions that remains is what if you cannot do obfuscation? Obfuscation is a very hard problem. What happens, and you cannot do it just out of scratch, but maybe with a little bit hardware assistance you can do it. Maybe you can have some secure hardware, which is not everything, but some secure hardware, maybe you can do things. So can we have a hardware-assisted obfuscation? So of course, if we don't make any restrictions on the hardware, then of course we can have a secure, put everything in secured hardware, be done with it. But can we minimize the security requirements from the hardware? And the hardware be very small. So there are some partial answers. So we can weakly obfuscate any program, given only just 1 out of 2 memory, simple memory. But this doesn't really give us full obfuscation. It would be nice to be able to do something like this. And another question is, so can you design a hardware that does it? Another question, can you use hardware that exists widely, like a TPM, right? That every computer have this secure chip, small chip. They could do secure obfuscation but only not loading the TPM too much. So this is a very good question, and I think it's a great research question. Yeah.
Sorry.
Yeah. Yeah.
So what do you mean by latency? Bandwidth being the number of bits exchanged between the TPM chip and your software code is small.
Right.
What do you mean by latency?
So the chip, assume the chip is slow. This TPM is slow. So you don't want to wait for it too much. Okay. You do things on the side. Yeah. Okay. So this is one set of questions about hardware security, and some other questions natural, I think, kind of more high-level questions. So can we have, so with this virtual black box or even virtual gray box, we can only obfuscate very simple functionalities, very specific functionalities. Can we have some generic obfuscation algorithm that really can obfuscate everything, or maybe almost everything, or whatever, some larger class of programs with some reasonable notion of security? So we know that we know that V will be for everything we can't, but maybe something else. And the sad thing is that we don't even have candidates. It's not that I have candidates, I don't know how to prove they're secure, find the right notion. I don't even have candidates that does anything meaningful and in a generic way. So we used in crypto, we always go on the circuit, gate by gate, we do this, we do that, we always can get everything, right? But here it doesn't seem to work. So this going gate by gate, it seems kind of inherently doomed to failure somehow. Because really what you want to hide is the internal intermediate values of the computation. So can we do anything? So fully homomorphic encryption sounds like a great thing, and maybe you can use it, but I don't know. Another direction is, can we come with a set of cryptographic tools that will help practical obfuscation problems? Those people out there that want to obfuscate code, those vendors, can we have tools that can help them come up with better products that really can be used? So that's another set of questions. And another one is, can we, this obfuscation lens, this different way of looking at cryptographic problems, maybe it can give us some understanding about cryptography in general. So that's it. Thank you. Yeah.
Ron, can you go back to your definition slide, way back?
Okay.
I was confused about the alternate definition you gave, and maybe I'm just misunderstanding the quantification.
Just a second.
Yeah.
This one?
Yeah, the or equivalent, is that over all possible input? So all possible input distributions?
So it's for any program. So the way I wrote it here was there was no family here, it was just for any program in general. But if you want to do something which is achievable, you want to fix a family of programs, and now you want to say that for any program in the family, this should happen. So you fix a program in the family, and these two random variables, or these two probabilities, should be the same.
Again, maybe I'm misunderstanding, but isn't it the case that I've got a family of programs, each of which produces 1 on 50% of its inputs? Mm-hmm. It's very easy to simulate producing 1 on 50% of its inputs, but not really simulating the program if I do that.
No, but so there's one specific program that's out there that output, so let's say in the hyperplane, the functionality, the program has a hyperplane, and you give it input, gives you yes if it's here or no if it's there, if it's above or below, whatever. So maybe that's learnable, so that's not very good. But so some function like this. But you have a hyperplane hidden in this program, right? So somehow, and this adversary gets access to this program or to obfuscated program and tries to find some interesting bits. So if this hyperplane is the first coordinate, is it even odd or something? Yeah. And this is what it tries to do. And the simulator should be able to do the same thing, but just oracle access to the program. So this program has the hyperplane written here there somewhere, and can answer messages yes or no, above, below.
But the overall probability of 1, I can match.
No, right, the overall, but there's one specific adversary, and for any adversary they choose the simulator. So there's a program and there's an adversary that tries to put one specific property or predicate of this particular program. So this pinpoints the bit.
Okay.
Okay.
Yeah. Maybe last question before the TBA main setups.
Can you separate the two definitions, VBV and VGB?
So we can separate them for those things that kind of hidden under the carpet. So we can separate them for So just a second, I'm trying to figure out which way it goes. So we can separate them for for the circuit model, but we cannot separate them for the Turing machine model.
So specifically, there is a program which can be obfuscated under VGB definition. It cannot be obfuscated under VGB definition.
Yeah. In particular, this program that, in fact, for the circuit, look at this family of programs from the BGI thing, right? For the circuit model. This program is actually trivially obfuscatable in the VGB model. Just because you can break the encryption, whatever, by... That's because in the circuit model. In the Turing machine model, I don't know. So in fact, it's a good question about the difference between the two. It could very well be, for all we know, that any program can be obfuscated, VGB obfuscated in the circuit model.
It's probably we should take the main questions up. Sorry. The main questions. So run is here, so
Thanks, yeah.
So basically, I want to talk about outsourcing computation. I know there's another talk just like a couple after mine with the same words in the title, and I hope that's okay since this is a cloud crypto workshop, and there's bound to be some redundancy in that area. But I want to talk about it, outsourcing computation privately, verifiably, and perhaps even practically. So first of all, privately, as you may have guessed, I'd like to talk a little bit about fully homomorphic encryption, but not in as much detail as usual, since I'm a little tired of talking about it. But basically, the problem is that you have some client with an input, and you have a server, and the client would like to delegate the computation, and furthermore, she would like to delegate it in such a way that the cloud doesn't even see what her input is. Okay? So that means basically that she wants to encrypt her input so to make it private from the cloud. And then somehow, despite the fact that it's encrypted, you would hope that's the case for any function f that's chosen either by the cloud or the client or whatever. It's possible for the cloud, without the secret key, to compute something that looks like the encryption of f of x. Okay? And then at that point, the cloud just sends it to the client, and the client uses her decryption key to recover f of x. Okay, so this is a fully homomorphic encryption scheme. In the past, it was called privacy homomorphism, but nowadays we call it homomorphic encryption. And the fully just means that we would really like it to work for every possible function f there that can be expressed as a Boolean circuit, say. In the past, there were plenty of schemes that worked for some subsets, some small class of functions. But the fully, we would like it to work for all functions. So a bit more formally, a homomorphic encryption scheme has the usual algorithms of an encryption scheme, keygen, encrypt, and decrypt. And it has this additional algorithm, eval, which is, again, a public algorithm. It doesn't take the secret key as input. It just takes some ciphertext and a function, and it outputs another ciphertext which encrypts the function applied to the input. And what we would like, a property of that final ciphertext there is compactness. There have been some schemes in the past where if you kind of operate on the ciphertext, the resulting ciphertext grows and grows and grows and grows until it's really, really huge. What you like is that the encryption of f of x there, let's assume that f of x is a single bit, the output of a Boolean circuit. You would like that ciphertext to be a nice, compact, normal-looking ciphertext, so that it's really fast to decrypt it and recover the output. And the point is we want to delegate processing, and if for some reason it took a really long time to decrypt this output ciphertext, that wouldn't be any good. We want the recovery time to be kind of independent of how much computation was involved in computing f. Okay? And the notion of security is just the usual notion of security. It's just semantic security. That it should be hard to tell whether a 0 or 1 is encrypted. And I just had to throw these slides in here because I love them so much. I like to describe homomorphic encryption in terms of a physical analogy. So you can see that, kind of it works in the real world in some sense. So the physical analogy I have is that you have a jewelry store owner, Alice, and she has some raw materials. And what she would like is to delegate to some workers that she has the processing of these raw materials into rings and necklaces. Okay? So this is what we want him to do. But she's worried about theft, right? If she just willy-nilly gives the workers the raw materials, she might lose some of her raw materials. So she's worried about theft. So in some sense, she has an analogous problem to the homomorphic encryption context. She would like a worker to process the raw materials without giving away complete access to the raw materials. Okay? And the solution here is kind of an encryption glove box. So you have Alice creates this glove box with a lock on it, and to do this, she puts the raw materials in the box, and she sends that over to the worker. And the worker sticks his hand inside and assembles the ring while it's inside the box. And he, let's assume the box is impenetrable, so it's kind of useless to him. So he sends it back to Alice, and Alice just uses her decryption key to unlock it and recover the finished piece. So that's basically the delegation of computation scenario that we want here to get out of our encryption scheme. Essentially, the homomorphic property is the gloves. Most encryption schemes don't have gloves that allow you to manipulate what's inside. Okay, so now suppose you had a fully homomorphic encryption scheme. So how would you solve, like, maybe a typical cloud computing problem? So suppose, for example, that I just encrypt all my files. I put them out on the cloud. And at some later point, I want to retrieve some particular files, some files that have some combination of keywords. So what I do is I just encrypt the original files with this homomorphic encryption scheme. Okay, and then later I have some query I want to make, and that query can be expressed as some Boolean circuit, basically. Okay, so you just encode that query, and then the cloud just operates on the encrypted data that's sitting on its servers, combines it with the function f, and runs this evaluation algorithm, essentially processing the data while it's inside the encryption box. And what comes out is a ciphertext that is supposed to, by definition, encrypt f applied to the messages inside those original ciphertexts there. And that's what I wanted, right? That I wanted, basically, that's the response to my query. That should be precisely the files that satisfy the particular constraint of having these keywords. Okay, and so there are lots of potential applications of fully homomorphic encryption. You could do an encrypted Bing search, for example. This is very theoretical. You wouldn't. It would take a really long time to do this. But in principle, you could I could just take the bits of my query and encrypt them. Okay, and then if Bing agreed to, then it could just take my encrypted query, combine it with all the data that's sitting here and whatever search function it uses, and come up with a ciphertext that is responsive to my query. Okay, and it would never see what my query was. This would be very slow, so I'm not claiming it's practical or anything, but in principle it's doable.
Is fully homomorphic encryption somehow contradicting the conventional wisdoms that for natural queries like searching, you don't look at the entire, if you organize it in a data structure, you don't have to look at the entire data? Because here, if everything is encrypted,
yeah, so it's kind of doubly inefficient, not just the fact that everything is encrypted, but also that in practice you would use indices to make the search go blazingly fast, some sort of, if you imagine a binary search type thing. But if everything is encrypted, you can't really do a binary search on the data because you can't see anything, you're just doing everything kind of blindly.
It would be interesting to maybe characterize, this kind of efficiency limitations that you will buy by privacy, because I haven't seen it formally. Intuitively it's clear that you cannot do binary search and things like that, but I haven't seen formally what exactly is the price.
Yeah, that's true. That hasn't really been formalized. But basically, the idea is that when you try to encode binary search as a circuit, what it ends up looking like is, well, the circuit has to touch all of the data. I mean, it's some static thing that just has to touch all the data, and that's what the homomorphic encryption scheme is run on. It's run on the circuit that's of size linear in the data, even though in principle a binary search on unencrypted data could be log time.
Homomorphic encryption on PRAM would be great, but it's not clear what it is. So.
Yeah. Okay, so some other applications, private information retrieval. I'll talk about that later, but basically the idea is that you just want one little slot of information without telling the database which slot you just picked. Searching encrypted data, that's basically what I was talking about there. There are other approaches using things like pairings, but this is, with fully homomorphic encryption, it's a bit more flexible because you don't have to pre-specify some sort of keywords that you're going to search for. You can just do it dynamically. Can also do things like have an access control mechanism that's kind of oblivious. I can encrypt my credentials and offer them to the server, and the server can take these encrypted credentials and offer me back some information only if my credentials satisfy some constraint. But of course, it would be operating on these encrypted credentials. It wouldn't even know what exactly they are. And there are various other good things that homomorphic encryption does for two-party and multi-party computation. So it was recognized early on that this would be a very useful thing, this privacy homomorphism. Basically right after the invention of RSA, and their motivation is basically similar to ours now, searching on encrypted data. And over time there have been plenty of somewhat homomorphic schemes, like an RSA, if you just very, very basic RSA, if you just multiply two RSA ciphertexts under the same key, what you get is a ciphertext that essentially encrypts the product of the original messages. And so you can do a multiplication operation inside the encryption box. So it's multiplicatively homomorphic. But there's no way to do an add operation. And really, to do general functions, you need, basically, if you look at AND gates and OR gates and so forth, all of these can be expressed as some combination of additions and multiplications. So if you can just do additions and multiplications sort of indefinitely, then that's really all you need for fully homomorphic encryption. But we didn't have that. We had schemes that did one operation. And here's a scheme that does quadratic formulas. And as I kind of alluded to, there are other homomorphic encryption schemes that, in principle, you can evaluate the ciphertext forever. But the ciphertext just expands and gets bigger and bigger, so even exponentially with the depth of the circuit. So they're not really very practical. Okay, so now we have some fully homomorphic encryption schemes. We have 3 of them now. All of them basically use the same blueprint, which is a little disappointing. And I'll talk about this blueprint later. And this blueprint is kind of inherently slow. So therein lies the problem. We have a solution, but it's a bit impractical because they all use this blueprint, and we don't have any other way of doing it. So I'll get back to this, but I want to talk about one more application that I was involved with of Fhe, and that is this idea of outsourcing computation verifiably, not just privately, but verifiably. And here the setting is, again, you have a client that wants to delegate the computation to the cloud, but she wants a quick way to check the cloud's work. Of course, she could, just duplicate the cloud's work if she wanted to take the time, just make sure it's the same. But the point is, she wants to spend much, much less time than it would take to do the work herself. Okay? And so here we have, is kind of somewhat analogous setup. We have some input x and a function f, and the server puts in a lot of work, and it outputs f of x, something that looks like f of x and kind of a proof that this is indeed the correct value, f of x. Okay. And the client just verifies that the proof is correct. Unfortunately, homomorphic encryption doesn't solve this problem immediately because, I mean, the server can do all sorts of computations on encrypted data, but how do you know at the end that it encrypts the results you want as opposed to just, you know, the cloud just created a fresh ciphertext that encrypts whatever it wants? You have no idea. So a bit more formally, so a verifiable computation scheme has four algorithms also. There's a keygen algorithm, but in this case, the keygen algorithm depends on the particular function f that the server wants to be computed. Okay, the function f can be like a universal circuit. So a universal circuit can take some description of a function f as well as an input, and then it'll output this function applied to this input. So it's not, when I say it's constrained to a particular function, that sounds very limiting. But in fact, that can be a universal circuit which would allow you to encode any function. So second, we have a problem-generating algorithm, which is sort of like an encryption scheme, except it uses the secret key that Alice hides. Okay? And then there's a computing algorithm where basically the worker takes whatever the output of the problem was and just kind of manipulates it and outputs some answer. And then finally there's a verification algorithm which includes, it's kind of like analogous to decryption in some sense. I mean, she takes the output of the worker and kind of decodes it and sees if it's the right thing or not, verifies the proof. Okay, and again, we want a compactness property here. We want that the output of the worker is nice and short, and so that it's very fast to check it. Okay, hopefully independent of the function and size. And security, what we want is, well, basically no bad proofs, that it's impossible for an adversary to output some y prime and a proof that, you know, y prime is indeed f of x when it's not the case. And even in this setting, it would be nice to have some input privacy, although that's not really part of the definition. I mean, you can imagine that Alice, you know, just as originally would want to keep her input private, but we're not demanding that here. That would be just kind of a feature. So for this, there are lots of applications. So, I mean, there are many reasons you'd want to check that the cloud performs correctly, even protect against benign errors. If the data is very important, it's going to be used in some other computation or financial transaction. You want to protect even against benign errors. For small devices, maybe a small device would like to outsource its computation. There you just have sort of the same issues. In large-scale computations, like SETI at home and folding at home, there you need to weed out the bad results before they're incorporated, obviously. And if the results weren't verifiable, there might be a strong incentive for users to fake them. So there are plenty of kind of ad hoc solutions to this. One is just redundancy. For example, at folding at home, you just have multiple people compute the same thing. Take a majority. And there are various audit-based solutions that, I mean, the client itself, or, you know, like folding at home, can recalculate some portions itself, just to make sure that it's correct. And there are various kind of secure hardware solutions, but they don't really completely solve the problem. In terms of more theoretical crypto work, there's, you know, a long line of work beginning with interactive proofs, where the idea is that you have a powerful prover trying to convince a verifier of something that it can't do on its own. These are interactive. We kind of want to avoid interactive solutions. There are probabilistically checkable proofs. So there you can have a computation that's, it's a very long computation, and it has a very long proof of correctness. But what you can do is encode this proof of correctness in a PCP way, which means that the verifier can just take portions of the proof, and as long as the prover doesn't know which portions of the proof beforehand, which portions of the proof the verifier is going to pick, then it's basically stuck, and the verifier just checks these portions, and then it's satisfied with some probability. You also have efficient arguments and CS proofs. And there, basically, there's you sort of overlay some crypto on top of a PC proof. The prover sort of commits cryptographically to its PC proof. And in the case of CS proofs, the challenge, kind of the query by the verifier, is done non-interactively by using a random oracle. Okay, so the prover applies a random oracle to its own proof, and which is kind of hard for the prover to predict what it is, and that says which bits of the proof the prover has to give to the verifier. Okay. And so, yeah, so in all of these schemes, there's really no notion of privacy of the data, which would seem like a pretty important aspect in a lot of scenarios. Okay, so I want to talk, I guess, very briefly. Well, I think I have at least 10 extra minutes. About a recent solution that we have using fully homomorphic encryption to this problem. And what we have is a non-interactive, efficient, verifiable computation scheme for every function f without these PCP-based solutions that we had in the past. And furthermore, there are no random oracles. I mean, random oracles don't really exist, so that's kind of an impediment to their acceptance. So the size of the worker's response grows only linearly with the output of the function of f. That obviously is the best you can possibly hope for. Whereas in the case of the PCP-based proofs, I mean, there's some higher dependence. It's still not very high, but it's a little higher than just plain old linear. And we get input privacy for free because, well, we're using fully homomorphic encryption, so that's what you would expect. So there is a drawback of this scheme, and that is that if you want a function, you have this function f, and you're going to be receiving multiple different inputs for it over time, and you're going to want to evaluate it dynamically at that time. But it's going to be the same function f. Okay? So we have this amortized notion of complexity here, where basically for this function f, there's a one-time setup procedure, which is kind of expensive for the client. It takes as long as computing f. But once that is done, the subsequent evaluations of f, the client will receive this benefit of the verifiable computation scheme, that it'll just have to do a short verification work on what the worker sends to it. Okay? And there's one other drawback, and that is, okay, suppose somebody cheats, okay? So I receive a proof that doesn't verify. What do I do then? So unfortunately, in this scheme, if you detect that someone's cheated, you basically have to stop at that point, and you can't use what you created in this one-time preprocessing phase anymore. You have to create another one. Okay? Okay, so here's the high-level idea. It's a very simple idea. I hope it's not too simple, but the idea is basically take a one-time verifiable computation scheme. Okay, in this case, you're only going to compute the function f once. Okay, and it's pretty obvious. We have a one-time verification scheme, and that's Yale's garbled circuit, which I'll describe in just a minute. Okay, but for some reason that I'll get to in a minute, trying to reuse this Yale garbled circuit is not secure at all. Okay, but it's secure once. Okay. So you take that one-time scheme and you basically sprinkle some Fhe on top. And so what we'll do is, like, if you want to evaluate F repeated times, each time you generate a new Fhe public key. And instead of just sending the YAO input wire labels in the clear, which is what you would do up here, you encrypt them under that fresh homomorphic encryption public key. Okay? And then what happens, I mean, what would happen in the original scheme is that the user would kind of evaluate the YAO garbled circuit and get some label for an output wire. Okay? So here the worker does the same thing, but it's all inside the homomorphic encryption scheme. Okay? So, I mean, you know, any function that you can evaluate, you can sort of evaluate inside the homomorphic encryption scheme. That's kind of the point. And so you just evaluate that entire garbled circuit while inside the fully homomorphic encryption scheme. And the worker ends up with an encryption of the bits of a YAO label instead of the YAO label itself. And the client just decrypts that, checks that it's a good label. Okay. So just to review, in case you don't know, so here's the YAO's garbled circuit. So you have some function f that you want to compute. You express as a Boolean circuit with and or NOT gates. And then you have a lot of gates that look like this, that have 2 inputs and 1 output. And you associate to each wire in the circuit a couple of labels, like strings, say 100-bit strings. Okay? Or 128, just to be precise. And then to each gate in the circuit, you associate some ciphertext, 4 ciphertexts. And what this ciphertext is, for example, is what it means is that you'll recover basically the output wire. Let's say the operation is an AND. The AND of 0 and 0 is 0. So G00 here is going to be 0. So you will recover C0 if you have the labels A0 and B0. Okay? If you happen to, so as you percolate through the circuit, you're going to have exactly 1 label at each wire. Okay? And if you happen to have A0 and B0, then you can go here and you can decrypt this ciphertext and you can recover C0. Okay? But if you have A0 and B0 and you try to decrypt anything else, you're going to have a problem because there's going to be some label that you don't know. For example, B1 here. So that means you won't be able to recover C of 0, 1, except for the case in AND. It happens to be the same thing, but you wouldn't know that. Okay? And then you publish these ciphertexts in random order, so it's unclear which are associated to which wires. Okay, so to use this as a let me see what my next slide is. So to use this as a one-time scheme, so basically the client takes the circuit associated to the function f that it wants to evaluate, and it creates a garbled circuit for it. And when it has a particular input that it wants to be evaluated for f, well, that's associated to, 1 label for each wire. It gives those labels to the worker. The worker just percolates up through the YAO garbled circuit, and it gets the label for some output wire, and that's the answer. Okay, and intuitively, the reason this is not clear is that, the only way that the worker could forge is if it somehow output the other, if it figured out what the other output label for the output wire is. But how is it going to figure that out if it doesn't, it's not able to decrypt those other ciphertexts in the garbled circuit, which it shouldn't be able to. So that's it's basically the intuition. But, so that's why it can be used as a one-time scheme, but now imagine you try to use it twice. Okay, so I've already given the worker basically half of the input labels for the YAO garbled circuit in the first round. Now, if there's a different input, and I give him the labels for those, the associated labels in round 2, then at this point he has like 3/4 of the labels, and eventually he's going to sort of collect all of the labels for the input wires, both for 0 and for 1. And if he has all of those labels, then he can basically unravel the whole circuit. It's not garbled anymore at that point. Okay? And it becomes insecure. So that's why we can't reuse it. Okay? It just has to be used once. Otherwise the security argument breaks down. Okay? So, again, our solution is really very simple. It's so simple it can just be put in a nice little picture like that. It's just to homomorphically encrypt under a public key that's specific to the round all of these particular labels. And, again, the user just kind of does the same thing he did before in the one-time scheme, except all the action happens inside the fully homomorphic encryption scheme, so that it gets a homomorphically encrypted label at the output, either C0 or C1.
There should be a pointer. Oh, you'd rather use that than reach up.
Oh, okay. I like the hands-on approach. And the intuition of the proof is basically, okay, basically, let's say the worker cheats successfully in the scheme. Okay, there must be basically some round for which he outputs a proof that's incorrect with respect to some input. Okay, so let's just guess which round the worker cheats on then. Okay, we'll be right of some reasonably good probability because there are only so many rounds. And then in the other rounds, we just replace the homomorphically encrypted stuff that we would normally validly create with just kind of random junk. And obviously that's kind of useless to the attacker. It shouldn't help the attacker. And so once we've done that, really all the information that the attacker is getting is what he correctly got in that one round that we've targeted. And so that means that if he can break the scheme, for that one round, essentially he's breaking the one-time scheme, the one-time YAO scheme. That's a very hand-wavy description of the proof, obviously, but that's basically the intuition. Okay, so but what if the worker tries to cheat? Okay, we know he can't cheat once, but let's suppose he's responded with something that didn't verify properly. Okay, we've caught him. We didn't accept his output, but now what do we do? Okay, can we continue? And the problem is no, we can't really continue because here's an actual attack that the worker could do to gradually unravel the entire garbled circuit inside. Okay, so here's what the worker is going to try to figure out what each YAO label is. Okay, so what it does is, in the round, it's given a homomorphically encrypted label. It just zeroizes one of the bits. So it replaces one of those ciphertexts with an encryption of 0 and sees if that messes things up. Okay, it does everything normally after that, sends back a response, and if the client says, oh, that's bad, then that means, oh, that must have been encrypting a 1, not a 0. And so in that way, since it kind of gets a bit of information from the client in each round as to whether it verified properly or not, a malicious worker can gradually figure out what the labels are and then just destroy the entire circuit. So what's the countermeasure? Well, basically after you detect cheating, you have to start with a new garbled circuit. It's not quite as bad as it sounds because you could have a situation like unfolding at home where it constructs a garbled circuit for that day, and maybe it has millions of users. So it creates one garbled circuit for millions of users to work on that one day. And then it's just not going to give any verification information through that day. So it'll receive all these responses from users, but it won't say whether it verified or not. So it won't give any information back to the users. And then at the end of the day, it'll do some accounting procedure where it says, okay, those responses you gave me were kind of screwed up, and I'm not going to pay you for those. And then it starts over the next day with a new garbled circuit. So as long as this verification information that goes out always occurs after all of the client's verification work has been done, then everything is fine. So you can still get some amortization benefit here, even though it doesn't work as well as you would hope. So it would be nice to have better countermeasures, though, so that's an interesting open problem. And I'm running low on time. So I want to talk a little bit about practicality with the Fhe scheme, though. And this is also an interesting open problem. So we have, as I mentioned, we have 3 Fhe schemes now. They all follow the same blueprint, which is the following. You construct a somewhat homomorphic encryption scheme. That means a scheme that maybe you can do additions and multiplications on the underlying plaintext for a while, but then maybe it gets stuck for some reason. Okay, so it can go on it can compute functions of some complexity. And then in the blueprint, the idea is to take this, hopefully you can take this somewhat homomorphic encryption scheme and kind of like beat it down until it has a certain property called bootstrapability, which is that what you would like, for a reason that I'll tell you in a moment, is that the encryption scheme, it has some class of functions that it can evaluate homomorphically. And what you would like is that the decryption function of the encryption scheme itself is in that class. It's kind of like a self-referential property of the encryption scheme. Okay? And this is a property I call bootstrapability. And, well, I'll just go to the next bullet. It turns out that if you have this property, if the somewhat homomorphic encryption scheme has this property, that it can kind of homomorphically evaluate its own decryption function and still get a correct result at the end, then it's easy to transform that scheme into a fully homomorphic encryption scheme. This is a general transformation. So yeah, so the idea in the second step is that you just try to massage this initial somewhat homomorphic encryption scheme so that its decryption function becomes like flatter and flatter, can be expressed by a flatter and flatter circuit. And once it becomes flat enough, then the scheme becomes bootstrappable because the decryption function is finally in the set of functions that the scheme can evaluate. So anyway, all the schemes follow this basic blueprint. And as you might imagine, this blueprint inevitably leads to slowness because it involves homomorphically evaluating the decryption function. So the decryption function on its own in this scheme is kind of slow, okay? But let's imagine that you have a decryption function that's expressed as a circuit with lots of bits on the wires. What you're doing here is you're homomorphically evaluating the decryption function. That means you replace each of these bits on the wires with some huge ciphertext. Okay? So you're kind of like squaring the complexity of the scheme. It's like the complexity of the decryption function times the size of the ciphertext in some sense. So it's kind of inherently inefficient. And so one natural question to ask is there another blueprint? Another question is maybe bootstrapping is not really necessary. Maybe if you just look at the somewhat homomorphic encryption scheme, maybe it does a good job at evaluating most of the functions that we're interested in. So why do we only have this particular blueprint? I don't know. Speaking for myself, I can say I was looking at a lattice-based encryption scheme that was quite homomorphic. You could do a good number of additions and multiplications, so it was interesting. And each ciphertext has some noise associated to it. There's just abstractly there's some noise parameter associated to the ciphertext. And as you add and multiply the ciphertext, it has the effect of growing this noise until the noise basically drowns out the signal. The ciphertext becomes indecipherable. Okay, so the question arises how to reduce the noise of a ciphertext. So you'd like to take a ciphertext that has some kind of large noise, and you'd like to somehow refresh the ciphertext so that you get another ciphertext. It encrypts the same thing as the original one, but it has smaller noise, so that you can combine it with other ciphertext for a little while until that noise gets too big, and then you refresh again. And so you continually refresh the ciphertext. And that just happened to, the way to refresh ciphertext just happened to be to kind of homomorphically apply the decryption function. So, I mean, if you just apply the decryption function, of course, it would, then you would just totally you decrypt it, and you create a totally new ciphertext that encrypts the same thing that has small noise. Well, that's easy, but obviously, we don't want to give away the decryption function. But it turns out if you homomorphically apply the decryption function, it has a lot of the same effect. So this particular scheme had some noise in it, and the bootstrapping just arose out of how to solve this noise problem. But in the past, people have typically investigated schemes that didn't really have any noise associated to them. So there's this line of research started by Koblitz and fellows, where basically, well, I won't go too much into it, but basically an encryption of 0 is like an element of some algebraic ideal. An encryption of 1 is like 1 plus some element in the ideal. And so as you add two things in the ideal, you get another thing in the ideal. That's like adding 0 to 0 to get 0. And all the other operations work out. And see, there's no noise associated here. It's just a question of whether the element is in the ideal or not. It's called the ideal membership problem. And if that's hard, then you would get a fully homomorphic encryption scheme if you could get everything to work efficiently. But unfortunately, these schemes have the problem that I mentioned before. That is, you add and multiply ciphertexts. Basically, the individual ciphertexts are multivariate polynomials. And as you add and multiply them, they're multivariate with lots more monomials than the original ones, and they just expand, get really large. And so for this second question of can we avoid bootstrapping, maybe many functions we don't even need it, I just want to give you, we've actually implemented this scheme. So I want to give you some motivation for this question. So if you just look at a somewhat homomorphic encryption scheme, where we're just doing kind of simple additions and multiplications of ciphertext that induce additions and multiplications on the underlying plaintext without the refreshing step, you can see things aren't so bad. I mean, we have, this is kind of increasing security parameters. Okay, we have, you can see the public key is kind of large here. Okay, it's not great. I'm not saying it's great. But the running times are, milliseconds and seconds, right? It's not totally ridiculous. But if you go to the fully homomorphic scheme where we have this refresh procedure, what you see is that for like moderate sizes, just refreshing a single ciphertext over here takes a really long time, like 3 minutes. So if we could avoid that, that would be fabulous. And I think I'm really over time now, but there are a couple of interesting settings where the polynomials, some interesting polynomials, for example, in the private information retrieval context, where a client just wants to extract the ith bit of a database without telling what I is. And like keyword search, where you just want to find if a particular string is in the file. These are two examples of where the polynomial that's being evaluated is actually really low degree. Not really low degree, but low enough so that really bootstrapping is not going to be needed. And so it would be interesting to look for other, try to categorize the types of functions that don't need bootstrapping.
The BIR, do you have a BIR based on homomorphic encryptions that runs in like seconds? So
no, we didn't implement that. Okay, so there are many open questions. I'm sure some of you know there's a DARPA BAA for relating to computing unencrypted data. So they're offering $20 million in funding. And they're focusing on speeding up FHE. And I'd like to encourage you not to apply. All right, that's it.
guess we still have 2-3 minutes before the next session, so feel free to ask seriously one quick question maybe. Alright, so we have a non-zero break, and I guess the organizers maybe like 11:20, 10 minutes, so 11:15 maybe?
11:15?
11:15.